So our next speaker is Vasil Dimitrov, who is a member of my group in Torino. And he will talk about exploring thermal black holes in a precise ADS-5 CFT4 setup.
Okay, yeah. So first of all, thanks to our organizers for putting up this great conference. I will be telling you about work in progress that I've been doing with Samir Murthy on thermal black holes. But I really like to stress that this is work in progress, and I would specify what we are sure of, or like very confident in, and what needs further analysis. Good. So the setup that we're placing ourselves in is ADS-5 CFT4, and on your left you have supersymmetric and extremal black hole, which has this ADS2 throat in the near horizon region, and you know what to do. Okay, this is like spectacular successes of holography. Good. So now on the right hand side, you turn on a small temperature, and this squiggly line is and then you get the ADS2 throat turns into a nearly ADS2, and you get this squiggly line which is supposed to represent the Schwarzian mode in the asymptotic region of the ADS2. And now the question that I want to ask is, does the CFT4 know anything about this Schwarzian? Or of course it knows, but like how do you get it out of? Except maybe by running to Ellie and asking her to bootstrap the whole thing. But if I don't do that, what can I do? Good. So I have my my 5-dimensional black hole due to those people right here, and it's a non-supersymmetric, not extremal black hole, specified by 4 parameters, which are plus, Q, and B, which roughly correspond to mass, electric charge, and 2 angular momenta. But the relationship between these black hole parameters and the charges is a nonlinear relationship. It's not like one-to-one. And here I have given you one example of how, for example, the inverse temperature is related to these black hole parameters, in which you write your supergravity solution in terms of. Good. So what has been done previously is you want to take this non-supersymmetric solution and you want to go to supersymmetry, or more specifically, you want to go to the BPS locus. And what was realized by those people right here is that in order to match with the results in the superconformal index, what you first have to do is go to supersymmetry, at which point you have to accept and embrace that you have to work with complex potentials due to this I right here. And then you you drive beta to infinity in such a way that you keep this little omega constant, and you end up at the BPS locus. Okay? And good, but there are infinitely many ways to reach the BPS locus. And I'm not going to go all the way. I'm not going to reach exactly the BPS locus. I would instead want to go nearby its vicinity. And, okay, what can I do? I take all of these parameters, not just Q, like all of the 4 parameters that I showed you before, and I expand them with some parameters T and epsilon, which I collectively denote by S, standing for small. And these are these coefficients which we fix by demanding that T represents the inverse beta, and epsilon, we would like to think of some independent SUSY deviation, okay, independent of this parameter T. And I'm going to comment on the significance of this relation in a second, but before that, I would just flash you the result of this procedure, where now you have your entropy, which is given by the BPS result plus a correction, which is first order. And similarly, and by the way, there is a mass scale appearing here, which would be important later on. It's just the characteristic mass scale at which corrections start appearing. And the action, similarly, is the BPS action. By the way, stars, everywhere you see star, it means BPS, not complex conjugation. So this is the BPS action. And then it gets corrected, but it doesn't get corrected at first order, the action. It gets corrected at 0th order, and this X here would play an important role. It's just epsilon over T. Okay? Good. So let me mention the significance of this. The balancing condition before implied that sum of potentials is equal to 2 pi IT. Okay, that was a revelation a few years ago. But now we are replacing this with it equals to 2 pi IT plus epsilon. And I have color-coded in red what is complex. You see that in the first equation, because these three objects are complex, there is no way for T to not be complex. So that is one way to see that in the supersymmetric case, T is not representing some physical temperature, but instead is representing just the length of an S1. So this is like it's just a parameter in the theory, it's not a physical temperature. However, now with this modification, which appears at first order, I can certainly design my limit towards the BPS point such that epsilon and T are both real, and this relationship is still satisfied. Okay? And equivalently, if I take this relationship and I rewrite it in terms of these parameters omega that you saw before, you get something like this. So basically, a parameter omega, which I would start from now on calling field theory fugacities, even though I'm still talking in gravity, but they would be eventually associated with field theory fugacities. So let me start calling them fugacities right now. So these fugacities are given from the expansion by BPS fugacities and an order 0 correction, which is a known expression of the sigma star, which I'm introducing now. I do not give you the expression, but it's a relatively simple known expression. It's just not particularly enlightening. Good. So, but what I want you to notice is that notice what gets modified at which order. So the balancing condition got modified at first order, whereas the BPS bound, which says that this linear combination of charges is 0 when you're supersymmetric, it stops being 0 at second order. Okay, and that would be important. At second order in epsilon and T, as you can see from here. Good. Diagrammatically, what do? We take the full black hole, which is not supersymmetric, and we go close to the BPS locus. And once we're here, what we can do is we take this parameter x. Now, every expression here will depend on x. And we can take this parameter and we can make small x to go more towards supersymmetry, or to take large x and go more towards extremality. By the way, it's a good place for me to mention that this mass scale is not something that we came up with. It has been previously identified in these papers right here to be this particular expression in terms of the parameters of the black hole that I showed you before. Good. So let me take some time to rewrite and like slightly elaborate on the result of the on-shell action that we are getting. So I can rewrite it. You stare at the expressions. It's a nasty expression in terms of A and B. With a little bit of effort, you stare at it, and you realize that you can repackage it in terms of these omega stars and sigma stars. Okay? So far, nothing interesting has happened. What I really want is to take this gravity result and write it as much as possible in field theory language. I want to write it as much as possible in terms of field theory fugacities. So I don't want omega star or sigma star. Like, maybe I have some interpretation of them in field theory, but I don't know what it is. I want omega. And I try, and the best one can do is you almost write it in terms of this language, and the deviation from being able to write it entirely as an expression of omegas is captured by these functions G2 and G1, which again I have explicit expressions for, but they are not particularly enlightening or interesting. Good. I need to mention some classical statements about the partition function, Casimir energy, and index to avoid confusion. So I'm working on a classical level. So I approximate the partition function as just exponent of the on-shell action of the leading saddle. I don't consider other saddles. And now I take this partition function and I just rewrite it like this. I'm allowed to split it into a Casimir energy contribution and an indexing quotation type contribution. And from here, we can use a standard formula to express the Casimir energy, to extract it out of this approximated partition function. And what you notice is that the Casimir energy is entirely written in terms of field theory variables at this point. Okay? This is just an observation. I will skip this, it's not important for us. Now I will take a little bit of time to connect to the pictures that I showed you at the very first slide. So the near horizon geometry of like any black hole, what you have to do is you have to go close, you have to bring the temperature to 0, and simultaneously you have to bring an observer towards the near horizon. Now we throw epsilon in the game, and we have a similar prescription of how to obtain the near horizon geometry. And you do that, and what you get is the near ADS2 that I promised you. You get an S3, you get some non-trivial fibering between them, and you get some scale factors. What happens is that once you reduce on the S3, you end up with an effective theory on ADS2, which eventually you relate to the Schwarzian theory, and all of work that people have previously been doing. We have just prepared for this analysis by including epsilon as well as an independent parameter, not just t. As an aside, I want to mention that mimicking to what used to be happening at for the charges, the equations of motion and the SUSY variations hold to first order in this near horizon geometry. Good. So let's go to field theory now. I'm in 4 dimensions, so I make sure that I relate the asymptotics of my black hole, of my near BPS black hole, to the correct 4-dimensional space, 4-dimensional background, which is locally supersymmetric, aka satisfies the Killing-Spinor equations for absolutely any value of epsilon. Supersymmetry, however, is broken, and it is broken by boundary conditions. So, like, you just amend the boundary conditions by beta epsilon, and this is what is breaking supersymmetry. As an aside, again, let me mention that this background has been studied before. It's what's known as a Hopf surface, and it looks like S3 fibered over S1. Some expressions about how this fibration is happening, and it has a complex Killing vector, which is given by this expression. Okay? Good. So this is a packed slide, so let me unpack it for you. I want to do a Cardy limit, which is an established procedure. And that Cardy limit is I take this S1 to be small compared to the S3, and then I have a procedure that I have to follow. First, I have to relate the 4D background fields to the 3D background fields. Then, I have to construct, like I would end up with a 3D Chern-Simons theory, 3D effective Chern-Simons theory. And then I have to construct, like Chern-Simons pieces. I have to supersymmetrize them, and evaluate them on the background that we were considering. And then I have to take their coefficients and determine them by integrating a tower of massive KK modes with certain masses. And finally, I have to sum over the Oda fermion towers and evaluate the dominant saddle. Okay, this is the procedure, and because I'm low on time, I would be quick. First result is that from the matching, you obtain that the 3D background does not explicitly depend on epsilon. Okay, it depends on epsilon only through sigma 1 and sigma 2. The explicit dependence on epsilon cancels, and so this result is important because it means that I can borrow results from, for example, Kasani-Kumargotki and other papers, which evaluate those Chern-Simons actions from me, and they obtain these expressions right here. Then, in steps 3 and 4, there is a technical issue related with the fact that due to the corrections that I have made, this real mass that I have to be summing over now is complex. So what do? One of the very simplest things that you can do is you take this sine m that you have to sum over and replace it with sine of real m. Okay? I'm happy to discuss of how legit this procedure is. I would flash you the result if I do that, and I get a Chern-Simons result, which is corrected, for example, compared to what I showed you from Kasani-Kumargotki by the appearance of this X right here. Good. And then you import from gravity the field theory-like result for the corrected Casimir energy. At which point you obtain a QFT prediction for the partition function. And, okay, let's compare with gravity. Trace R cubed is equal to proportional to 1 over G. And looking at the expressions, well, they don't match. Okay, there is these functions G1 and G2, which I didn't know what to do with. However, what you can do is you can take this parameter x and study what happens for small and for large x. For small x, what happens is you recover BPS results, nothing surprising here. So far, so good. For large x, however, they also agree. And the proportionality constant that appears here is precisely this 1 over m, which is this mass scale identified in the papers that I showed you before, which now here I have just rewritten in terms of the variables that naturally come out of this problem. But this expression right here is precisely equivalent to, so many slides ago, to write this thing here. Okay, so now I promised you a disclaimer, so here is the disclaimer. One needs to do an independent QFT calculation of the Casimir energy. One needs to justify this, and I have some ideas of how to justify it, but I'm working on them. And there are questions about freedom to choose regularization, renormalization scheme in gravity, because when there is supersymmetry, there is some intuition that we know what the renormalization scheme should be. Now I'm no longer supersymmetric, so what renormalization scheme should I be using? And finally, should we even be expecting these things to match? I mean, on gravity, I'm doing T to 0. In the field theory, I'm doing inverse T to 0. Okay, so why should these things match? And even further, a priori, nothing is protected. As soon as epsilon is away from 0, there is no protection whatsoever. However, we see some indication that when we're not SUSY but extremal, something seems to be holding. And there is some relation with very recent work of Cabot-Bizet, Alejandro Cabot-Bizet, who is performing similar computation in field theory, not from the perspective of the effective 3D Chern-Simons theory that I was using, but directly by considering weakly coupled n equals 4 super Young mules and performing some of like similarly looking manipulations. But honestly, I need to speak to him to understand exactly what he's doing. Okay, thank you.
Thank you. Thank you. Questions? Carlos.
They need to do some regulation on, so they have to some infinite Caluster length, right?
Yeah.
You also have the same
Yes.
regulation, and you choose their same regulation. They do a particular way of regularizing. So it's an infinite sum, so it has to be regulated.
Yeah, so the infinite sum is like you take this expression m, set x to 0, which for their case it's 0, and then it's just zeta function regularization. And actually it's a zeta function, and the regularization was performed by Di Pietro and Komargotsky before them. It's the same regularization. And so here, as soon as I demand this, I actually don't need to change the regularization. As soon as if I don't demand this, I might need to worry, and yeah.
More questions? Okay, what? Yeah, go.
In their case about the Chern-Simons being level n. So they summon this Caluster length to get the Chern-Simons coefficient. Right? And there was something special about when it was the case level n. Is there anything like that happening for you? I understand you're doing a different calculation.
Right. Yeah, I'm not sure what, but if you tell me later on in private, because the calculation that I'm doing is mimicking theirs in like as much as possible.
Nikolai.
It would not be the first time.
near radius 2.
Yeah.
But as you told us at the beginning, there's this approach where you first impose SUSY in Euclidean, and then you don't have an ADS2 region at all. Can you say something about these two things? How do you reconcile them? Like, suppose I'm somewhere at finite beta, BPS, sorry, supersymmetric.
Yeah. So I'm like in the diagram and somewhere.
Right. I should not be able to use the Schwarzian.
Here.
Right? Because then I don't have ADS2 at all, right?
Yeah. So I mean, like the way I understand it now is that at this point, to use the Schwarzian, you need a small parameter which is somehow related to some temperature. Okay, and right here, beta is a complex number which can be arbitrarily large, and I don't know how to interpret it as anything which is related to the Schwarzian. So I need to go close to the BPS point. I want to be really close to BPS. I don't want to be only supersymmetric. To be able to relate to Schwarzian arguments at all.
So is the claim that if you are at this other point, then you would not see this universal linear behavior with
Yes.
T and universal 1 over m behavior that you emphasize?
Yes.
Is this the expectation?
That's precise. I mean, like everything is going to be some more complicated expression of, yeah.
Just a small comment about, in the end you mentioned, you were talking about the renormalization scheme, which you mentioned, you presumably you don't know how to handle it in the non-supersymmetric case.
Yeah.
But my understanding is the renormalization scheme you're using should not depend on the solution, right? So especially if you're comparing to the supersymmetric case, you should be using the same one.
Right. Yeah. So indeed, thank you for the question. What I meant by choosing renormalization scheme is, of course, the finite counter terms. So I was choosing the exact same one, right? But in principle, if I don't have supersymmetry, I could choose a counter term, and I would not know how to fix it. And indeed, it would make sense to choose it such that I'm comparing to the BPS point.
More questions? I have one last, just general question. So this is nice because you're going non-supersymmetric in ADS5. Maybe in 4 dimensions would be easier. Is there anything to learn in 4 dimensions to do this?
Right. So what I can say is that the gravity procedure of like every time you have, like we've seen many examples now where you have to use complex fugacities for like supergravity solutions when they're extremal, when they're supersymmetric, and every time this happens, I can apply a similar procedure in gravity. In field theory, I wouldn't know yet how to do it, but I presume this is just taking the limit, like that should be possible for every black hole.
Thank you, and then let's thank Vasco again.